Hello and welcome to Unit 2, where we're going to talk about antigens, antibodies, and vaccines. Let's go ahead and start with a few terms. Antigen, this is also known as an immunogen. This is a protein marker on the surface of a cell that identifies the cell as self or non-self. Antigens are capable of provoking an immune response. Okay, what I mean by that is you're going to see symptoms in your patient, and your patient is also going to make antibodies. Okay, an antigenic determinant is combining sites or epitopes, structures or molecular components on the membrane of a cell that are recognized as foreign. A determinant group is sites on or within an antigen in which antibodies will react. The number of these sites is the valence. So antigens are multivalent. This means they have many sites for which antibodies can react with. Let's go ahead and talk about the cellular antigens of clinical importance. And these are the antigens that are clinically important and can elicit an immune response. Okay, the first one on the list are the HLAs, the human leukocyte antigens. They're also known as histocompatibility antigens, and they're present on nucleated cells. They are present on many nucleated cells, not just leukocytes. HLAs include the histocompatibility antigens and are part of the major histocompatibility complex. This complex mediates the interactions of white cells and other cells. Major histocompatibility complex antigens determine organ transplant compatibility. They're probably the second most important clinically significant antigen right after the blood group antigens. Okay, that brings us to autoantigens, and these are antigens that produce autoantibodies. Then we have our blood group antigens, or the markers on blood cells, and then we have microbial antigens, and those would be antigens on bacteria, viruses, toxins, and toxoids. There are several properties that actually make an antigen. These properties are both physical and chemical and make up an antigen. Okay, foreignness is one of the properties that makes up an antigen. And that's the degree the immune system recognizes the molecule as being self or non-self. So the more the body recognizes it as being non-self, the more foreign it is. An antigen must be present long enough to trigger an immune response. So in other words, it must be present long enough to trigger the formation of an antibody. That's called degradability. So you don't want something that degrades too fast. If it degrades too fast, it's not a good antigen. Good antigens have a high molecular weight, usually greater than 10,000 Daltons. They are structurally stable. If the molecule is too weak, it's not going to make a good antigen. And they are complex. The more complex an antigen is, the more effective it's going to be at eliciting an immune response. And then also antigens are protein or large polysaccharide structures. Usually antigens are protein in nature. We have three types of antigens. We've got the autoantigens, which are self-antigens. These are antigens that elicit the formation of autoantibodies. We have alloantigens, which are foreign material from the same species. So an example of that might be your blood group antigens from donor cells. We have heteroantigens, which are plant, microorganism, or chemical antigens. This is an antigen that originates outside of one's own body. Let's go ahead and talk about an antigen's role, or what I mean by that is the criteria which an antigen must fulfill. It must induce the formation of antibodies and react specifically with the antibody that caused it to be produced. If it doesn't do those two things, then it's not an antigen. Let's talk about some substances that are good antigenically. And what I mean by that is that they meet all of the criteria that make something an antigen. And some of those that are good antigens would be bacterial antigens, and that would be antigens on cell walls, flagella, and capsules. We have toxins. Toxins make good antigens. These are poisonous substances of plants or animal origin. We have viral antigens, and then toxoids. A toxoid is a detoxified toxin often used to make vaccines. It can still elicit an antibody response but not make us sick, or elicit the formation of antibodies without making us sick. Then we have the poor antigens, things that make poor antigens, and that would be carbohydrates. Okay, they are too small to be good antigenically. We have lipids. that are poor by themselves, but if you link them to a protein, they function more antigenically. And then we have nucleic acids. So again, this slide covers all those things that don't meet the criteria for something to be an antigen. A hapten is basically a partial antigen. It reacts with antibodies, but it cannot induce the formation of antibodies. I'll say that again. It acts antigenically, but it cannot induce the formation of antibodies. And I'll give you a couple examples of that. Urushiol, which is a toxin associated with poison ivy, and hydralazine, which is a blood pressure lowering drug that can also act as a hapten. So both urushiol and hydralazine are haptens. Vaccines will elicit the formation of antibodies, and vaccines are made a number of different ways. They are made from killed organisms. An example of that would be the whooping cough vaccine, or Bordetella pertussis. Vaccines can be made from altered live agents, and that's called an attenuated vaccine. An example of that is the MMR, the measles, mumps, and rubella vaccine. Vaccines can also be made from detoxified toxins. Those are called toxoids, and one such toxoid is the tetanus vaccine, and this happens to be a toxin that was deactivated with heat and chemicals. And then finally, the fourth way a vaccine can be made is by using fractionated materials. So you can actually take parts of the original organism and use those materials to make the vaccine. One example of that is Haemophilus influenza vaccine. On this slide, I've just tried to give you different examples of vaccines that are made by killed organisms, vaccines that are made by altered live agents, vaccines that are made from toxoids, and vaccines that are made from fractionated material. So in the first column there, some vaccines that are made from killed organisms would be things like Yersinia, that's the bug that causes the plague. Bordetella causes whooping cough, and then you have influenza, rabies, typhoid, and autogenous vaccines, which is a vaccine made from a patient's own cultured bacteria. Then you have the altered live agents, which are the attenuated agents. The measles, mumps, and rubella vaccine is made from an attenuated virus. We also have the smallpox vaccine and the polio vaccine. Those are made from altered live agents. We have toxoids, which are exotoxins treated with heats or acids, and those toxoid vaccines are the diphtheria vaccine, the botulism vaccine, and the tetanus vaccine. Diphtheria is Corynebacterium diphtheriae, and then botulism and tetanus are caused from Clostridium species. And then finally, in the fourth column, you can see there we have vaccines that are made from fractionated material, or vaccines that are made from parts of the original organism. Some examples would be Streptococcus pneumoniae, hepatitis B virus, Haemophilus influenza type B, and also HPV, which is human papillomavirus vaccine. So this brings us to the production of antibodies, which is known as our third line of defense. So far we've talked about our first line of defense, which is body systems and natural barriers, and then we talked our second line of defense, which is inflammation and phagocytosis. And now we're going to start talking about our third line of defense, which is the production of antibodies. So let's start with the term, and that term is antibody. It's an immunoglobulin formed to combine with an antigen and neutralize its effects. Antibody formation, like I said, is the third line of defense. Our adaptive immunity is when the third line of defense has actually kicked in, and this consists of both cellular and humoral components. Some of the cellular components would be T lymphocytes and phagocytes. Your humoral components would be antibodies, or immunoglobulins, and complement. This adaptive immunity allows the body to recognize, remember, and respond to an antigen. It leaves the host with an immunological memory, thus the host can respond to antigens quicker the next time they're exposed to that antigen. There's a number of different types of immunity. I want to first talk about natural resistance, also known as non-susceptibility. This is absolute protection from a disease. For example, man is not susceptible to most animal diseases. Then we have natural immunity. This is the immunity that you're born with, and this is highly influenced by your heritage or race. Then we have acquired immunity, and we have two types of acquired immunity, passive acquired immunity and active acquired immunity. In passive acquired immunity, you've become immune to something because you have IgG that came from mom and crossed the placenta, or you have passive immunity because you had IgA from breast milk as a baby, or IgG injections. Active acquired immunity means that you've had the disease or you've had a vaccination. Cell-mediated immunity is sensitized T cells that protects us from bacteria, viral, and fungal infections, while humoral immunity has to do with B cells that make antibody. Also, complement is a type of humoral immunity. Let's go ahead and compare humoral versus cellular mediated immunity. You can see there that humoral immunity is antibody mediated. It involves the B cells. The mode of action is antibodies in your serum or other body fluids, and the purpose is to defend the body against some bacterial and viral infections. Cell-mediated immunity is cell-mediated. The T cell, or the type of cell usually involved in this cell-mediated immunity, are the T cells. The mode of action is cell-to-cell contact or soluble products from cells, in other words, what's released from the granules of cells. And the purpose of cell-mediated immunity is to protect a person from viral, fungal, intracellular bacteria, tumor antigens, and graft rejections. So let's go ahead and compare active acquired immunity versus passive acquired immunity. Okay? So in active acquired immunity, the source of that immunity is yourself. In other words, you've had the disease and you're making antibodies, or you had the vaccine and you're making antibodies. It is highly effective. Again, you either had the disease or you were vaccinated. It takes about 5 to 15 days before you start making antibodies to these agents that you've been exposed to. The duration is very long. You can be immune to something for years and years. You can get a booster shot. For example, the diphtheria, tetanus, and pertussis. You'll get an immune shot, or you'll get a booster shot for that, and that's pretty easy. And active immunity means that it is used prophylactically. In other words, to protect you from getting sick from a second exposure or an initial exposure to a disease. Okay? Passive acquired immunity, the source is another human or animal. So in other words, you got IgG from mom that crossed the placenta, or you got IgA from breast milk, or you got an injection of gamma globulin. The effectiveness is moderate to low. And again, the method of acquisition is either placental transfer, breast milk, or an injection of gamma globulin. The time to develop is immediately, but the duration is short. You're only immune for weeks to months. Ease of reactivation is actually dangerous. If you're given a second or third dose of gamma globulin, that can actually lead to renal failure, thrombosis, or tachycardia. And the uses of passive acquired immunity is either therapeutic or prophylactic. So let's see if you can tell the difference between passive acquired immunity and active acquired immunity. So if you've been administered a hepatitis vaccine, that's an example of active. It means that you're making antibodies in response to a vaccine. If you've recovered from viral pneumonia, that is active. You've had the disease. If you've been given an injection of gamma globulin, that would be a passive acquired immunity. Recovery from the measles and rabies vaccine, those are both active. You've either had the disease or you've been vaccinated. If you've been given the tetanus antitoxin, this is passive. Anti means antibody was injected, and antitoxin means gamma globulin was injected. Whooping cough vaccine, again, if you've had the vaccine, that's active acquired immunity. If you've had salmonella and you're recovering from salmonella, that is active acquired immunity. Let's go to the next slide and do a few more. If you've been given immune serum, that is passive. Immune serum is another name for gamma globulin. If you've been given a prophylactic serum for hepatitis, let's say you've been exposed to hepatitis, they gave you gamma globulin, that's passive acquired immunity. If you've had the vaccine for polio, that is active acquired immunity. If you have an elevated titer of anti-hepatitis B surface antibody, that's active acquired immunity. That means you've had the disease. If you've had an injection of diphtheria toxoid, that is going to be active. Toxoid is a vaccine. Toxin, an antitoxin, is passive. A toxoid is vaccine. Recovery from the mumps is active acquired immunity. Administration of the tetanus anti-serum. Again, you've been given the antibody. That's a passive type of acquired immunity. And then finally, an elevated titer of anti-salmonella H. That means you're making antibodies to salmonella because you had the disease. That is active acquired immunity. So, good job. So sometimes being given an injection of IgG will actually limit the seriousness and length of the disease. And this slide outlines some of the diseases where it might be beneficial to get gamma globulin. And I'll let you look these over, okay? Just for fun, I thought you might like to know when your immunizations are recommended that you get them. So at birth, they do recommend that you start the series for hepatitis B. I think they're even giving the hepatitis A vaccine in some cases as well, depending on where you live, which country you live in. But usually at birth, they give you the first round of hepatitis B. At 1 to 4 months, they give you the second dose of hepatitis B vaccine, and then at 6 to 18 months, they give you the third dose of hepatitis B vaccine. That's what they're recommending anyway. At 1 to 4 months, they give you the diphtheria, tetanus, and pertussis, Haemophilus influenza type B, IPV and PCV, which is pneumococcal vaccine, rotavirus vaccine, and the list just goes on. And I'll just let you take a look at that. And on this slide, I basically have outlined vaccines, the agent that causes the disease you're protected from, and the type of vaccine that a person would get. So in the case of diphtheria, if you have diphtheria, the agent that causes the disease is Corynebacterium diphtheriae, and it could be avoided by getting the toxoid vaccine. Whooping cough is caused by Bordetella pertussis, and the vaccine is a killed bacteria. Tetanus is caused from Clostridium tetani, and it's a toxoid vaccine. Okay, and I'll just let you look those over on your own. Be prepared to give me an example of these. Now, the ability to form antibodies depends on a number of things. First of all, the nature of the antigen. All of those physical and chemical properties that we talked about earlier. So your antigen has to meet all of those criteria in order for the body to make antibodies to it. Okay. Another thing that could basically change your ability to form antibodies would be the dosage or mode of administration. So in other words, how are you exposed? Did you get a vaccine? Did you have the disease? Was it placental transfer? All of that mode of administration and the dosage will basically determine how well you can form antibodies to it. Okay. And then finally, characteristics of the hosts themselves, their age, their disease state, and their state of nutrition. All of those things will influence how well a person forms antibodies. Antibody response. So there are two types of antibody response. There's the primary antibody response, and usually it's your IgM antibody that starts to rise first. And then you have a secondary antibody response. It's usually the IgG antibody class that starts to respond. Okay? So IgM are antibodies that are formed upon first exposure to an antigen, and IgG is an antibody that is made due to subsequent exposures, and this is called an anamnestic response or a memory response. There are 4 phases of immunoglobulin response once exposed to an antigen. There's the lag phase, where there's no detectable antibody in serum. There's the log phase, where the antibody titer starts to rise logarithmically. There's the plateau phase, where the titer starts to stabilize. And then finally, there's the decline phase, where the antibody is catabolized. And these phases look a little bit differently depending on if we're talking about a primary antibody response versus a secondary antibody response. So as I go through these on the next 2 slides, you may want to just draw this out. So a primary antibody response involves IgM antibody. This response occurs in the acute phase of the disease. An antibody is detectable in serum or body fluids about 5 to 15 days later. In the lag phase, this period lasts for a few hours to days, so it's a pretty fast lag phase or a short lag phase. In the log phase, there's a sharp rise in IgM antibody. In the plateau phase, the IgM stabilizes, but it doesn't plateau for very long, and then there's a decline, and there is a sharp decline of IgM in the primary antibody response. In a secondary antibody response, T memory cells stimulate antibody production during this secondary antibody response, and this is mediated by IgG antibody. This response occurs in the convalescent stage of the disease. So there are some IgM antibodies that are present in the serum, but that's only there in very low amounts. The primary antibody here that you're going to see in the recovery stage is IgG. The lag phase shows a fast rise of about 1 to 3 days. It is actually slower than in a primary antibody response. The log phase also shows a fast rise. The plateau is pretty different than the primary antibody response. The plateau phase in a secondary antibody response remains high longer than a primary response. And then the decline phase of a secondary antibody response is a gradual decline. So here you can see primary response and a secondary response both have a sharp rise in the log phase. The plateau remains level longer in the secondary response, and in the primary response the decline is sharper than in the secondary response. So here I've compared primary antibody response to secondary antibody response. So the time after antigen exposure until immunoglobulin is detected in serum happens about 5 to 15 days later in a primary response and happens a little bit quicker in a secondary antibody response, and that's because of that anamnestic response. The major immunoglobulin detected in a primary response is IgM. The major antibody detected in a secondary response is IgG. The amount of immunoglobulin in the titer for a primary response is low, and in a secondary response that titer is higher. The time of duration until the duration of titer, how long you will be able to see a titer in the serum in a primary response is very short, and in the secondary response the duration of the titer is longer, and that has to do with the plateau stage. So it's a short plateau in a primary response and a longer plateau in a secondary response. Let's talk about immunoglobulins or antibodies now. These are glycoproteins synthesized by B cells. They can be found in plasma, serum, saliva, and tears. They are used by the immune system to neutralize bacteria and viruses. Antibodies contribute to immunity in 3 ways. They bind to pathogens, they stimulate macrophages, and they stimulate complement. B cells either become antibody-producing cells or memory cells. These memory cells are lymphocytes capable of responding to an antigen on its reintroduction to the host. Other B cells make antibodies found in mucous membranes, serum, saliva and tears, breast milk, and one that's not on your slide but should be cerebral spinal fluid. Okay? The major antibody class found in mucous membranes is IgA. The major class found in serum is IgG. Saliva, tears, and breast milk is IgA. And in cerebral spinal fluid is IgM. There are 5 classes of antibodies recognized in higher mammals. All are generally similar except a small portion on the tips of both the heavy and the light chain that are extremely variable. Each variant can bind to a different antigen. The 5 classes of antibodies are IgM, IgG, IgA, IgD, and IgE, and they're all named after the heavy chains. They're actually named after the Greek root mu, gamma, alpha, delta, and epsilon. They differ from each other in molecular weight and carbohydrate content. The basic immunoglobulin molecule is bifunctional. In other words, each arm can bind to a specific antigen and each region mediates binding the antibody to the host tissue. It's divided into two regions. The IgG molecule is a good example of an immunoglobulin monomer. The core of each antibody consists of a sequence of amino acid residues linked by a peptide bond. All antibodies have a basic polypeptide structure with a three-dimensional configuration. So here in this image you can see the long chains are called the heavy chains, and then the shorter chains on the outer left and outer right of the image are called the light chains. Each molecule is named after the heavy chain. So the heavy chain is going to be IgA, IgD, IgE, IgM, or IgG. Alpha, delta, epsilon, mu, or gamma. The light chains, which are the short chains there, are called kappa or lambda light chains. So let's talk about the components of an immunoglobulin and the regions, okay? The first region I want to talk about includes the light chain and the top of the heavy chain, and that's called the Fab region. Fragments antigen binding is what that means, and this is the molecule end that binds to an antigen and recognizes specific foreign objects. The next region I want to talk about is called the FC region, or fragments crystallizable, and that includes only the bottom portion of the heavy chain. It binds serum complement, directs the biological activity of the immunoglobulin, and dictates if molecules can cross the placenta. It also mediates different physiological activities of the immunoglobulin. And then finally we have the FD region, which stands for fragment determinant, and that includes the top portion of the heavy chain only. The heavy chain of the Fab region is the FD region, and it determines immunoglobulin specificity and carries genetic factors. The immunoglobulin also has what's known as a constant region and a variable region. So the variable region is the first one I want to talk about because that's just the tips of the heavy chain and the light chain. Okay? And those are variable amino acids. It makes the molecule have a certain specificity to certain antigen. Okay? The constant region is the bottom portion of the heavy chain and the bottom portion of the light chain, and it is constant in every different immunoglobulin. Now, the light chain and the heavy chain are linked together by disulfide bonds, and the heavy chain is linked to the heavy chain in the hinge region by disulfide bonds. It makes the molecule flexible, and it's allowed to change shapes to access awkward binding sites. So we have 5 classes of heavy chains. There are 446 amino acids in the entire heavy chain. Amino acid 1 through 114 is variable, and amino acid 115 through 446 is constant. And I would suggest you take a look at the images in your book for this. Okay? The heavy chains are named gamma, alpha, mu, delta, and epsilon. The light chains are either kappa or lambda. You either have 2 kappa or 2 lambda. You never have one of each. And there's 214 amino acids in the light chains. 1 through 107 are variable, and 108 through 214 are constant. Let's go ahead and start by talking about IgG. IgG is the major class of antibody found in serum, and it consists of 2 light chains and 2 heavy chains. It appears in the serum about 6 to 7 days after exposure to an antigen, and it's the second class to form immunity. If you remember, a primary antibody response is associated with IgM, and a secondary antibody response is associated with IgG. IgG is the only immunoglobulin class that can cross the placenta. It's the only antibody that crosses the placenta from mom to fetus. Without it, newborns would have very little immune protection. The in vivo activities of IgG is that it fixes complement, it enhances phagocytosis, and it has antibacterial, antiviral, and antitoxin properties. Adult levels are reached by around 6 months of age. The in vitro activities: agglutination, hemagglutination, precipitation, and hemolysis. There are 4 subclasses: IgG1, IgG2, IgG3, and IgG4. IgG can be increased in cases of hepatitis, rubella, infectious mononucleosis, rheumatoid arthritis, systemic lupus erythematosus, and Hodgkin's lymphoma. 70 to 75% of all circulating globulins are IgG class. Some is also found in cord blood, and that would make sense because it does cross the placenta. IgM accounts for about 5 to 10% of the circulating globulin pool. It has 10 light chains and 10 heavy chains. It's a pentamer. There's 5 monomers held together by a J chain, and that J stands for joining chain. It allows IgM to cross mucous membranes. Okay? It's the largest molecular sized immunoglobulin, and it's polyvalent. It's the first antibody class detected after an exposure, and usually it starts to rise in the serum about 4 to 5 days after exposure to an antigen. Okay? And it won't cross the placenta like IgG does. There are 2 subclasses of IgM. We've got IgM1 and IgM2. The in vivo activities of IgM, they're antibacterial and will activate complement. It'll also enhance phagocytosis and macrophage activity. Some in vitro activities of IgM is agglutination and hemagglutination. What's really nice about IgM is that it's easily observed in these 2 types of serological procedures because the molecule is of such large size and has so many combining sites. Okay? It's elevated in cases of bacterial diseases, infectious mononucleosis, leprosy, malaria, and collagen disorders like scleroderma. IgA is primarily found in saliva and tears and mucous membranes. Okay. Also, it can be found in plasma cells of the respiratory tract and breast milk. Serum IgA is a monomer. What's pictured here is secretory IgA, which is a dimer. It's 2 monomers connected by a J chain. The J chain allows IgA and also IgM to be secreted in mucous membranes. IgA represents about 15 to 20% of the globulins. It's the second most abundant, even though much of it is found in places other than serum. Okay? It's found in body secretions and protects mucosal surfaces from bacterial invasion. Unlike IgG, it won't cross the placenta and it won't activate complement. Most is secreted. Most of it is secreted in the dimer form in saliva, tears, and mucous membranes. The secretory component of IgA is not bound to any protein in serum. The S component is derived from epithelial cells, not from plasma cells that synthesize the IgA in the first place. IgA couples with the secretory component just prior to secretion into the lumen. This protects IgA from digestion by GI enzymes. IgA synthesized by plasma cells in the mucosa-associated lymphoid tissue. As it passes through epithelial cells, it picks up the secretory component. The secretory component protects IgA from degradation by gastric enzymes in the mucosa of the GI tract. The least understood of all the antibodies is IgD, and even though it's the least understood, it may signal B cells to activate. It also may bind basophils and mast cells, activating them against respiratory diseases. There's only minute amounts in serum of less than 1%. Most IgD is found on the surface of unactivated B cells. It does not cross the placenta. It does not fix complement. And it's a monomer. It consists of 2 heavy chains and 2 light chains. And like I said, it may play a role in B cell development, but again, it is the least understood of all the antibody classes. Alright, finally we have come to the last antibody I want to talk about, and that's IgE. There's only minute amounts in serum of about 1% or so. Most is attached to tissue mast cells, and some is present in basophils. It's formed in the respiratory tract and GI lymphoid tissues. It's elevated in serum from patients that have allergies. It is responsible for allergic reactions. It does not cross the placenta. Does not fix complement, and it's monovalent. Only 1 combining site because it is a monomer. Alright, that's it. That brings us to the end of unit number 2. Stay tuned for unit number 3.